So to finish our work off in Chapter 8, we have that a medical research team conducted a study to test the effect of a cholesterol-reducing medication. At the end of the study, the researchers found that 4,700 randomly selected subjects who took the medication, 301 died of heart disease. There's an oven there that I can say. Of the 4,300 randomly selected who took the placebo, only 357 died of heart disease. At level of significance alpha equals 1%, they care very deeply about this one, can we conclude that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? So for this, as I've said many times, once you get the basic bit of comfort out of the way here, for the purposes of our problems, you can assume that we have the conditions we need, things are large enough, in this case they're definitely large enough, and we have properly independent and random information. To be sure, it's always worth a quick check, but for our purposes, it's more important to get the practice of the other things. So let's talk about how you get p-bar and q-bar, where it's good to know how to do this stuff as well, but truth be told, you're probably going to do most of the stuff with the two proportion z-test, two prop z-test in the calculator rather than do this by hand, but hey, can't hurt to see this process at least one more time, right? So, for p-bar, here we are actually given numbers instead of proportions. Makes our life a little bit easier for getting these things than the last one was, but it'll come back to bite us later. Anyway, this is going to have the flavor 301 plus 357 over the pretty big samples of 47 and 4,300. Got 9,000 people in there. That's a lot for one research study. But cholesterol is important. And that will give us an approximate value for p-bar of 0.073, about 7%, which means q-bar, its complement, is going to be about 93%. 0.927 to be a little bit more exacting. Then from there we can talk about our hypotheses and claim, where in this case we are given that we want to check if the death rate is lower for those who took the medication than those who took the placebo. So, like I said, there's a little bit of freedom in terms of how I want to define which one's P1, which one's P2. In this case, I'm going to define P1 as being attached to the people who took the medication, as I implicitly did right here with that X1, N1. But to be sure, you don't have to do that. You just should understand that a lot of the information you're going to be seeing, a lot of the conclusions you're going to be looking for will be flipped around. So for our purposes, for the way that I'm going to do this, I will say that our claim is that P1 is smaller than P2. That's what we're claiming. So the opposite of that is that P1 is at least as big as P2. That is, at least as many people died due to heart disease even if they took the medication. Kind of grim, but that's how medical studies usually go. Where this one gets to be the null hypothesis, and our claim gets to be the alternative. That's the very traditional way to have this. Anyway, with our hypotheses and claim, p-bar, q-bar, we can then get to our level of significance, which here is that given value alpha equals 1%, which, like I said, because it's pretty small, means that we really want to be sure about this. The smaller you make alpha, the more sure you want to be, essentially. And because of the way I set this up, I'm looking for P1 to be smaller than P2. This is a left-tailed test. But like I said, if I instead made P1 and accordingly X1 and N1 attached to the placebo, then I would be looking at P1 to be bigger than P2, and this would be a right-tailed test. That decision was completely arbitrary up to how I chose to use notation. And if I wanted to do it the other way, I would get basically the same problem. I'd just be looking for positive things instead of what I'm going to find here, hopefully, are negative ones. It really isn't a difference, except in framing. Just be careful with that. And be careful with that in the same way for the stuff earlier on in the chapter. It's a very, very subtle thing. It's not a very vital thing as far as the math goes, but you can end up in some very different places if you aren't careful. So, be careful, I guess. Anyway, with our level of significance in mind and the fact that this setup leads to a left-tailed test, we can then talk about, well, what we might want to do to, perform the test. Doing the tests usually matters. End up. And I'm going to follow the test statistic p-value way again, not because the critical value way is worse. I kind of do think it's worse, but just because it's a little cleaner and it leads the calculator a bit better. But for reference, if you wanted to get the critical value, you could see that the critical value follows something with an inverse normal computation, where in this case, you're looking for that 1% in the left tail and standard normal 0.1. So you get a value of approximately negative 2.33, another pretty standard value. And alternatively, if you're going to go out and do the proper computation for the test statistic z-score, you'd be plugging in those numbers into that formula. I'm not going to write it all out this time. It's not worth having all of those pieces written down because, again, it's more detailed than you really need in order to be able to get that z-value. I'm not going to ask you to get the z-value by hand very often. But anyway, that z-score here, pulling those numbers around, would be about negative 3.46. So if you wanted to see what this looked like on a distribution and kind of spoil the answer for yourself, you get something like this, where you can see how these things land up in there. But we're not the answer just yet. To be sure, though, we can then use that 2-proportion z-test computation in the calculator, run that on this stuff. We have to be very careful with the p's, because there's the p for the probability, there's the p for the proportion, there's the p hat for the other proportion, then there might even be the p bar for the other proportion. Just be careful with kerning there to identify the one you need, which in this case will end up being a very, very small p-value of approximately 0.0003. So less than 0.1%. It's a very, very small number. So even if we want to be really, really sure, still be pretty sure that this p-value is smaller than alpha. Or equivalently, as you can see from that spoiler, our test statistic z-score falls into the rejection region. That is, z is less than the critical value in a left-tailed test, where if we had flipped that around, like I said, z would then be positive and bigger than the positive one in the right tail. In either case, it's in our rejection region. P-value smaller than alpha, whichever we happen to like the most, whichever one we happen to be asked for in the moment, we end at the same place of rejecting the null hypothesis. We reject that statement, that the proportion of people who died, the death rate, it starts in proportion, that the death rate is at least as high for people who took the medication as it was for people who didn't, which is good news for that research team. It's good that they want to be very sure about it. Because what they can say, as a result, is something to the effect of, at the level of significance alpha equals 1%, there is enough evidence to support the claim that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo. Now, I do think maybe CDC and however other regulatory bodies you have for testing things might be a bit more thorough than one test like this, but this is the sort of evidence you'd want to see to know if a medication, a treatment, a vaccine is effective for what you'd want it to be. Anyway, like I said, this is all we're going to get for Chapter 8. It's not that much more complicated than things we've done before. New numbers, new pieces, same answers, really. So, next we're going to move into Chapter 9, which is going to be our last chapter of the semester, where we're going to talk about something a little bit different, We're going to see some pieces and put them into a context that is familiar, but a lot of what we're going to see with these things called regression and correlation will not quite fit into the same patterns that we've seen so far. But it's a nice introduction to something really important that the people who are going to go on with stats and work in the sciences, you guys need to see this at least once before you get on to the really important stuff that you'll see in your work. So that's what we finished the semester with, at least in my class. And that's where we will be starting in the next video. I'll see you in there.